Bismillahirrahmanirrahim. We'll continue with uh, the last meeting we have done with the hash diagram. The hash diagram. Here, this example shows how to draw the hash diagram and how to find the maximal and the minimal element of the diagram. The maximal element is the element which belongs to the set, okay, and there is no element above it. And the minimal element is the element which belongs to the set and there is no element below it. For example, you take this example here. You see this is a poset, the partial order set on division. Fine. Fine, and given is the hash diagram for this set. Now how it is drawn, you see it is on division, right? So the elements are 2, 4, 5, 10, 12, 20, 25. Starting from 2, what are the elements which can be divided by 2? Fine. You have the element next 4. 4 is divided by 2. Now, through 2, 4, then you have 5. 5 we cannot divide by 2 or by 4. So it is a separate element. Okay. Now, the next is 10. 10 can be divided by 5. 10 can also be divided by 2. Clear? Now, the next is 12. 12 can be divided by 2 by 4. Right? So, the line goes from 2 to 4 and 4 to 12. Fine? Then next 20. 20 can be divided by 2, by 4, by 5 and by 10. So, now here from 2, 4, 4 to 20. And then it can be divided by 5, 10. The next is 25. 25 is only divided by 5. This forms the hash diagram for the partial order set or the poset on division. Now in this poset, in this diagram, what is the maximal elements and what are the minimal elements? The minimal elements, you see, these are two minimum elements. There is no element minimum than this on division. There is no element less than 2 in this set on division. There is no element less than 5 which can divide 5 in this set. So, two elements you have for minimal, that is 2 and 5. Why we don't take 4? 4, we have an element which is less than 4 and can divide 4, that is 2. Okay. Now, the maximal elements, we have the maximal elements 12, 20 and 25. These are the maximal elements. There is no element above it to divide, which can be divided by these numbers. 12, forget 12. Above 12, there is no element which can be divided by 12. 20, there is no element above 20 which can be divided by 20. 25, there is no element above 25 which can be divided by 25. So the maximal elements are 12, 20 and 25. Fine. This is how to find the maximal and the minimal element from the given poset on relation from the hash diagram. Clear? Now coming to the greatest element and the least element. The greatest element, you see from this we say that A is the greatest element of the poset S relation if B relates with A for all B belongs to S. Now here the greatest element is an element which relates with all the other elements. which relates with all the other elements, and it is in the top in the diagram. For example, you see in this diagram the greatest element is D. This is the only element which is in the top on the relation. The greatest element is D. Here the greatest element is D. Fine. Here there is no greatest element. Why? Because there is more than one element in the same level. And here also there is no greatest element because there is more than one element in the same level. So here we are trying to find one element which is greatest from the maximal, one element which is greatest of all. So we have here in this diagram, this is greatest, in this diagram this is the greatest. In this diagram there is no greatest element, in this there is no greatest element. Fine. The next you have something called least element. Least is something called lowest element in the relation. So if you see in this example, A is the least element because it is the only element which is at the lowest, the minimum value, the only element. Here there is no least element because it has more than one in the same level. Here there is no least element, and here A is the least element. Clear? You got what is the greatest element and what is the least element? Fine. Now coming to the least upper bound and the greatest lower bound. Two things we have here: upper bound, least upper bound, lower bound, greatest lower bound. Fine. Consider this diagram. You have this kind of question in your homework also. The last question ask you to find the greatest and the lowest, the least and the greatest. It says the least upper bound and the greatest lower bound. Okay. Now this is the hash diagram for the poset 2, 4, 5, 10, 12, 20, 25 on division, on the relation division. Find the lower and the upper bounds of A, the set A 2, 4. This set A is from this set. Find the greatest lower bound and the least upper bound of A. Now you have to find the greatest lower bound of A, which is for this set, and the least upper bound of A, which is from this set. Okay. This is the hash diagram for the poset, this one. We have seen this before, how we draw this. Okay. Now the lower bound of A, the lower bound of A has 2, 4. MU موجود كيف اطلع هذا؟ فين؟ قول لي انا في المحاضرة. Fine. The the lower bound of A is 2. On the set A, the set A is 2 and 4. What is the lower bound in this one? We have 2, right? From 2 and 4. And the upper bounds. What are the upper bounds of 2 and 4? You have the upper bounds of 2 and 4. These are the upper bounds of 2 and 4. 4, 12 and 20. It is given in the question. A is a set, it is given in the question, not from your side. Okay. Now, what is the greatest of lower bound? The lower bound has only 2, and this is the greatest. If it is more than 1 in the lower bound, Okay, you can take the highest value in that. So greatest is 2. And what is the least upper bound? In the upper bound you have 4, that is 4, 12 and 20. So what is the least one? Is 4. The least one is 4. So this is how you find the greatest lower bound and the least upper bound. And this is what it is asked you in your homework in the last question, to find the greatest lower bound and the least upper bound. Okay, clear? This is what we have in this in this tutorial number 4, which talks about the relation. Okay, the next what we have is graphs. So in this tutorial or in this presentation, we are going to talk about the graphs, how to draw the graphs, what are the different terminologies related with the graph. Fine. We have some definition for the graph here. A graph is G, which is a set of V comma E. V is a set of vertices and E is a set of edges. So anything with a set of vertices and edges, we call it as a graph. So for example, these are the vertices. This is V, V1, V2. This is the vertices. And this is called the edge. For example, E1. So any graph has a set of vertices and a set of edges. So this graph, we can say it is a graph G, which has a set of vertices V1 comma V2 and the set of edges E1. So this is a graph which is this one. Fine. Clear? How we write this the graph? To write any graph, it is a G which has a set of V and E. V is a set of vertices. Vertices, for example, let's say this is a graph, what I draw here. It has A, B, C, D. And these are the edges. Let's say the edge is E1, E2, E3 and E4. Okay. Now what are the vertices? The set of vertices A, B, C, D. These are the vertices, the points which is connecting the edges. And what is the E? That is E1, E2, E3 and E4. This forms the graph G, which is this one. Clear? It's okay? The definition of graph. Fine. Here each edge has either one or two vertices associated called endpoints. These are the endpoints. An edge set to connect the endpoints. This edge is connecting the endpoints. Okay. So if the set of V of a graph may be infinite, in this we call it as an infinite graph. And if it is a finite vertices, if we have a finite vertices, we call it as a finite graph. Okay. Here it is given an example. This is a graph G, which is a set of V and E. Here what are the vertices you have? You have S, U, V, W, X, Y, Z. The points S, U, V, W, X, Y, Z. And what are the edges you have? You have XS, that is X to S. Okay, you have XV and XV1 1 and 2, because you have two edges. Okay, so all these connecting points, these are all the edges. You write it as a set. Fine. And this is called a finite graph because you have finite number of vertices, the fixed number of vertices. We call it as a finite graph. This is an example of a finite graph, which is a computer network which is connecting the cities. Okay. A simple graph, a graph in which each edge connects two different vertices and where no more than one edge connect the same pair of vertices. We call it as a simple graph. This one is a simple graph because 2 points, for example, to the San Francisco Denver is connected by only one edge, not by two edges. If it is connected by two edges, it is not a simple graph. Okay. So here it is a simple graph because every two vertices are connected by a single edge, by one edge. We call it as a simple graph. Simple graph. We have something called multi-graph where one edge is two vertices are connected by more than one edge.
Does it mean that two edge?
Which one? Hmm?
There's two lines.
Two lines. This one. These are two edges connecting the same point. And in one graph, if there are two edges connecting the same point, we call it as a multi-graph. If it is only one edge connecting the 2 points, it is a simple graph. So for example, if I have a graph something like this is a simple graph because every edge is every vertex is connected by one edge. If I have a graph something like this is a multi-graph because the edges are connected here by more than the vertices are connected by more than one edge. Okay, not fixed to, no, not all. If it is only even if it is a one edge, it is a multi-graph. Fine. Even this one, for example, this is a multi-graph because here we have two vertices and connecting by two edges. We call these two are multi-graph and this is a simple graph. Fine. Pseudograph where we have the loops in the vertices. We call that as a pseudograph. Salam rahmatullah. Shahid. جاء. خلاص عندك 59 وصلت الرسالة M359. شوف الايميلك ها ايميل الجامع. Okay. So when there is a loops, we call it as a pseudograph. Pseudograph. Loops in the vertices. Fine. We call it as a pseudograph. The next is directed graph. Directed graph, what is the difference between the simple graph and the directed graph? The directed graph has a direction in the edge. The edge is going from A to B. So there is a direction. Yeah, from A to B. Okay. So if it is only one edge or single edge from A to B, we call it as a simple directed graph. For example, this is a simple directed graph. I'll put this example here. For example, this one. This is a directed graph because there is a direction from vertex to another vertex. Let's say this is A, B, C. So this edge is from A to B. one way. It is not from B to A. It is from A to B. Okay. And you can draw also the other way, that is B to A. Okay. So you have only one from A to B. Yes, it is simple directed graph. Simple directed graph, because the edges are only one edge, not two edges. A to B is one, B to A is one.
Must give us an error, صح?
Yeah, it is something like this. It will give you an arrow.
So
If it does not give arrow,
arrow.
that is not directed graph. Two way it is. Okay. This is an example of simple directed graph. It is a one way graph. Now this is directed multigraph. Why? Because you see here, there are two edges from Chicago to Denver, two edges, and two edges from Denver to Chicago. So it is multigraph, directed multigraph. And in this table shows the graph terminologies. What is simple graph, multigraph, pseudograph, simple directed, directed multi, and the mixed graph. It shows what are the edges, whether it is directed or not directed. It shows multiple edges are allowed or not. That is, more than one edge from A to B is allowed or not, and the loops are allowed or not. Loops, no, loops is this one, looping to itself. These are the loops. Okay, so this table shows us all the details about the graph terminology, which is a directed graph, what it has, what is undirected graph, what it has, simple, simple directed, multi graph. Finally you have something called mixed graph, which is directed, undirected, which has multiple edges and which has loops, and everything is mixed up. There is a edge with a direction, there is a edge without direction, there is a loop, there is multiple edges also.
How's that?
A simple graph, for example.
Okay, but we can put a simple graph with multiple.
Yeah, adding together you can say. For example, this is, let's say this is A, B, C, D. So A to B has a direction, B to A has a direction, and then there is no direction. It also has multiple edges, it also has loops. This is a mixed graph.
But you said if we find two edges,
Hmm.
that's not directed, so
No, no, no. Directed, directed, not directed is only by using this direction.
sorry, not
Multi,
simple.
not simple graph.
Yeah.
Yes, if you have more than one edges.
Or mix with simple and multi.
Simple.
And multi, right?
See, this is a mixed graph.
And it's right up here.
It's right, yeah, it is a mixed graph. It is one type of graph. You have simple and directed, multi-directed, simple multi-graph, directed, simple directed, and directed multi-graph, and all mixing this pseudo-graph, and all mixing all this is a mixed graph. We will see some graph terminologies before we close, called adjacent, connects, endpoints, degree, initial, terminal, in degree, out degree, complete, complete bipartite, cycle, wheel, and n cubes. We'll see some of this one. For example, for an undirected graph, adjacency, let G be a graph with a set of edges E, where edge is from U to V. Okay, the vertex U and V are adjacent or neighbors or connected. And in the graph, this is U, this is V. Okay, and this is the edge connecting U and V. Okay, then we say that U and V are adjacent, adjacent or neighbors. Now they are nearer to each other. So we call it as an adjacent or neighbors or connected. They are connected. Okay. And the HE is incident with what is U and V. HE incident, it means meeting or connecting U and V. HE connects U and V. HE, this is HE, connects U and V. And U and V are endpoints of E. U and V are the endpoints for the E. Right? So these are the simple terminologies you need to understand. What is adjacency? What is adjacent? Adjacent, it means two vertices connecting. Okay. So we see that they are incident U and V. E is an incident with U and V. E connects U and V. U and V are the endpoints of E. Fine. Now degree of a vertex. Degree of a vertex. The degree of vertex V for any vertex, okay, is its number of incident edges, except that any self loop are counted twice. Any self loop are counted twice. Now what it is telling, degree of what is the number of incident edges. For example, this is an edge, let's say U. Sorry, this is an vertex, let's say U. You have two edges. Now what is the degree of U? How many adjacents are there? Sorry, how many incidents edges? 2, right? So we say the degree of U is 2, and 2 edges is connecting with that vertex. If we have a loop, it is counted twice, 2 times, and this become 4. For example, something like this. Say this is U, this is V. What is the degree of U? 1. V, degree of V? 1. If I have a loop here for U or for V, for example, what is the degree of U? 1. V? 3. Why? Because for any self loop we count it twice. Fine. A vertex with a degree 0 is isolated. Any vertex which is with a degree 0 is isolated. For example, this vertex, for example, U. This is isolated. No edge is incidenting or connecting. So it is isolate and its degree is 0. And a vertex with degree 1 is a pendant. Pendant. For example, this is this U and this is V. What is this? This vertex degree is 1. This is called pendant. And this is 1. This is also called pendant. Fine. Now handshaking theorem for to calculate the degree of the vertex is 2 into the number of edges connecting to it. Okay. Let G be a graph, be an undirected graph. Okay, it can be simple or multi or pseudo graph with edges. Then sum of degree of vertices is equal to sum of degree of all the vertices. All the vertices. For example, this, how many vertices we have? 3. Okay, let's say A, B, C. What is the degree of A? 2. B, C, 2. Now what is the degree of all the vertices? It is the sum of A plus B plus C, that is 6, which is equal to 2 into the number of edges. How many edges you have? 1, 2, 3. 2 into 3, 6. Fine. Now here is an example. How many edges are there in a graph with 10 vertices of degree 6? It is now you are it is the formula is sum of degree of vertices is equal to 2 into number of edges. Now the question is how many edges? You have to find this E.
12.
You have to find E.
A not 6.
So what is E? No, degree of 6. In the 10 vertices, 10 vertices, कुल है degree 6. Okay, यानी कम हैकुन 16. Sum हैकुन 16. यानी 10 vertices, every degree is 6. So total how many? 10 into 6, 60, right? So this is the formula. So how to calculate the edges is the degree, the sum of degree what is the formula? The sum of degree of vertices is equal to 2 into the number of edges, right? Now it is asked you to that there are 6 vertices, okay? Degree of every vertex is 10. Every vertex. So 6 V1, V2, V3, V4, V5, V6. 6 vertices. Every one degree is 10. So sum how much? 60. So the sum is 60, which is equal to 2 into the number of edges. So now number of edges is equal to 60 divided by 2, which is 30. So you have 30 edges
Divided or multiplied?
divided because you take it here. Cross multiplication. Fine. So you have 60 number of the degree of the total sum of the degree is 60. So therefore 60 is equal to 2 into E and E is equal to 30, which is so sum of what edges is equal to 60 divided by 2, which is 30. Fine. Now given is the graph and here are the degrees. For example, degree of A is 6. 1, 2, 3, 4 and the loop is 2. So 4 plus 2, 6. For B, 1, 2, 3, 4. Like this you calculate for all. And the sum of all the degree of vertices, you add all these. Okay? Which will be equal to 2 into the number of edges. Sum of all the degree of vertices is always equal to 2 into the number of edges. Okay? The vertices are A, B, C, D. In this graph, V is A, B, C, D, E, F and G. And the edges are A to B, B, C, like this. Okay? In a directed graph, we cannot count the opposite way. So the directed graph, how we can find the adjacency or how we can find the degree of a vertex in a directed graph. Now let us say in the directed graph there is a graph from U to V, the edge from U to V. Okay, we say U is adjacent to V and V is adjacent from U. U is adjacent to V and V is adjacent from U because it is single directed. Okay, and E comes from U, E goes to V. You see it is at one direction, right? So it is coming from U, and going to V. When E connects U to V, we cannot say V to U because it is the direction is from U to V. So we say that E connects from U to V or v E goes from u to v. Fine. E is this edge, this is E, and the initial vertex of E is u. Initial, it means the starting point of the edge. E is u, and the terminal is v. Terminal is the end point. Okay, it's clear. Right. The, if it is a directed graph, we have two degrees, two types of degree: the in degree and the out degree. The in degree and the out degree. For the undirected graph, we just say degree of a vertex. But here we have the in degree, we write it as degree minus v. That is the in degree, and the out degree is plus v. Out degree. Now, what is the in degree? Is the number of edges going to v, or reaching the v. So, for example, this is v 1, 2, 3. So, what is the in degree for v? It is 3. How many edges coming to v? 3. So, we say the in degree is 3. Out degree is opposite of it. Opposite. So, for example, it is going 1, 2, 3. So, what is the out degree? 3. Okay. The out degree here is the number of edges coming from v. So, how many edges that are coming from v? 1, 2, 3. Okay. This the out degree. Okay. Now, total degree we can say as the in degree plus the out degree. The total degree of v is the in degree plus the out degree. Okay. A loop at a vertex contributes 1 to both in degree and to out degree of the vertex. Now, here the loop is counted only 1, not 2 times. In the undirected graph, we count it twice, but here we count it only 1 time. Okay, clear? Now, the theorem here for the calculating the total, the sum of all the degree of vertices is given here. That is 1 by 2 into sum of all the vertices is equal to the number of edges. Okay, the total degree will be the in degree, which is equal to the out degree, which is equal to 1 by 2 for the total degree in plus out, which is will be equal to the number of edges. It will be number of edges. And note that the degree of a node is unchanged by whether we consider its edges to be directed or undirected. The degree of a node is unchanged by whether we consider it at the edge, its edge to be directed or undirected. Fine. That's clear. Clear. This formula is okay or not okay? The degree, the in degree is equal to the out. If it is equal to the out degree, then the total degree will be 1 by 2. 1 by 2 into in degree plus out degree. Okay, which is equal to the number of edges. I'll put one example here. Yes, this example, or this is a big example. I'll put a small example. This is u, this is v. Okay, this is the edge from u to v, and this is the edge from v to u. Now, what is the in degree of v? 1. What is the out degree of V? 1. Okay. What is the in degree of U? 1. And the out degree of U? 1. Okay. Now, if the in degree is equal to the out degree, okay, which is equal to 1 by 2 of the total degree. Total degree is what? 1 plus 1. What is the total degree of V? That is the in degree plus the out degree is the total degree, right? So it is in degree is 1 plus 1, it is 2, which is equal to 1 by 2, okay, of the total degree of V, which is equal to the number of edges. How many edges are there from U to V? Only one edge, right? So this is what the theorem given here. If the in degree is equal to the out degree, that will be equal to 1 by 2 of the total degree, which is equal to the number of edges, and the note is given that the degree of a node is unchanged by whether we consider the edges to be directed or undirected. How? We have seen here directed graph, undirected graph, right? Now, what is the degree of, if we consider this here undirected graph, we write it like this, for example, U and V. What is the degree of U? 2, right? Now, if we consider the degree of U here, for example, degree of U in the directed graph. What is the degree of U in the directed graph? Sum of in and out. Degree of in and the degree of out. So what is this? One is in and one is out. So it is 2, right? So even the node here, even if it is a directed graph or the indirected graph, the degree remains same. This is what the node given here, that the degree of a node is unchanged whether we consider the edges to be directed or undirected. But the only difference is in the undirected graph we don't write the in and out. In degree, out degree, we don't have in undirected graph. But in the directed graph we have the in degree and the out degree. But the total degree is same. Clear? This is an example of it, that the out degrees, and these are the in degrees.
Undirected, we don't write
The in degree and the out degree. Undirected graph we don't write the in and out because it is undirected, so there is no in and out. But in the directed graph we write the in and the out, okay? But still the total degree will be same. Why? Because it will be in and out, we'll bring it to again. Fine. The special graph structures, we'll stop here inshallah for the day, and we'll continue in the next meeting from the here. Okay. Finish. Yeah. Tabal note.
Without the
Undirected graph.
degree is U2.
A. This is undirected graph U to V. Okay. For what is the degree of U? 2, right? And degree of V? 2, right? Now, if we consider the same graph, a directed graph, for example, this is this is V, this is U. Okay. Now, what is the degree of U? Degree of u is degree of in degree plus out degree. So what is the in degree, what is the out degree? In, yeah, the out degree is 1 and the in degree is 1. So 1 plus 1, 2. And what is the degree of v? Again 2. 1 in and 1 out. 2. So even if it is a directed, undirected or a directed graph, the degree remains the same. Okay.
يعني في الكويشن will give us undirect on in the
ايه ممكن في السؤال ممكن في الكويشن they'll give you the graph and ask you to calculate the degree. If it is a directed graph, they may ask you to calculate the in degree, out degree, or the total degree, or they'll give you the example something like this. What we have seen the example. Yeah, this example, for example, they say that how many edges are there in a graph with 10 vertices of degree 6 each. So you have to use that formula, sum of all degrees equal to 2 into number of edges, and substitute the value to give it. Okay. So for today we'll stop here. Sorry. Not equal.
in and out.
It is not give you the number of edges. The number of edges will not be same.
So there is no edges, number of edges.
Sorry.
If not same,
Yeah, if
there
an
is no
in and
edges.
out is not same, okay, then we don't we will not get the same number of edges. Okay. Fine. Regarding the MTA grades, it is on the coordinator, so it is not in my hand. So I'll see if the coordinator when is she is going to publish it. Okay, might be in this week, inshallah. They'll publish it. Most of the courses they are publishing in this week. So I hope even you'll get in this week.